the Wheatstone Bridge, to talk about it as an interesting example of a circuit that is neither series nor parallel, that requires that you use Kirchhoff's laws exclusively in order to make any kind of solution to it. And generally, this problem tends to be, I don't want to say hard is the wrong word. It's just overly complicated. But there is no series or parallel here. The Wheatstone Bridge, though, it's a purposely designed circuit designed specifically to help you measure very precise resistances. And if you just were asked to solve this circuit, if I was to throw some values down here and ask you to figure out what the currents were, it can take a long time to do it, because if you just look at the picture there's a lot of potential loops here when it comes to doing Kirchhoff's rules. And with every loop, it generates one equation. So that's 3 equations for at least 3 loops. That's what it's going to take to get all those resistors. And then every junction generates its own set of equations. So you're going to need at least 3 junctions to get all the currents. So suddenly you've got 6 equations and 6 unknowns. And so this is a bear of a problem. This problem is never asked on the AP exam because of how time-consuming it is, but also because this is a very known problem. And what I mean is it's well known in the physics community. There are other ways to solve it, and there are quite readily available simple shortcuts to get to the answer. So this problem is seldom asked, but there is a related question to this that is asked very frequently. So again, this is the Wheatstone Bridge. This portion in here is called the bridge. But what I want you to consider before I redraw this a little neater is 2 specific loops. This one and this exterior loop. When we consider those 2 loops, what is often done with this circuit is this resistor is removed and replaced with either a capacitor, which makes this a far more manageable circuit, or it's replaced with a voltmeter. Now, a capacitor and a voltmeter both have the same effect on the circuit in the long term, because in the long term, this bridge has infinite resistance, whether it's a capacitor or whether it's a voltmeter, meaning that there's no current across that bridge. Measuring the voltage isn't nearly as hard as it sounds, because if we have a total EMF of, say, just V over here, I hope you guys have come to grips with the fact that no matter what these 2 resistors are here, we'll say R1 and R2, they're going to split that voltage proportional to the resistance. Similarly, on the other side, R3 and R4 are going to split the voltage proportional to that resistance. So there will be a voltage drop to this point and a voltage drop to this point that are governed by the ratios of R1 to R2 and R3 to R4. And unless those voltage drops are the same, it'll produce a voltage across the bridge. Now, it's sometimes hard to see that in a circuit drawn in this way. So luckily, almost every time this has been asked on the AP exam, they've drawn the circuit a little cleaner to make it a little easier for students. So let's do it like this. And I'm going to put some numbers to this just to get us kind of thinking. We're going to do 50 and 100. And we're going to do 100 and 150. There we go. And we'll do 100 volts here. Now, drawing it in this way, ignoring the bridge completely, is one method of considering how to solve this circuit. So what I'd like you to do, and I'll give you just a minute or two to do this, is I'd like you to go by and see if you can figure out what the voltage is for each of these in the current configuration. And we got a late start on this, so don't take too long to do this. I'm going to call you guys out in just a minute, but this shouldn't take you but a minute or so. Went about solving this. But from my looks at you guys, and I can only see a few of you, it looked like you guys were going about it the long way. You know, maybe figuring out that there was 150 ohms in one of the loops and then finding out the current. But there's a way to do it without ever finding out the current. And I'm hoping that you guys are starting to see that, because it will help make the work go a little faster, but also it will help with this problem. Look, V1 and V2, they're going to have to split that voltage up in an amount that's proportional to the resistances. 50 ohms is 1/3 of the total resistance in that leg. The total resistance is 150. So since 50 is 1/3 of the total, that means this voltage has to be 1/3 of the voltage, 33 volts. If I look at the other side, the total resistance is 250. 100 ohms is 40% of 250, right? 100 to 250 is 0.4. So that means this one had to be 40 volts, because it's 40% of the total voltage. Not having to find out current or anything there. But resistors in series are going to split up the voltage in a proportional way. Something that's proportional to their total resistance. So if you have a simple set of resistors in series, the voltages are going to play out this way. And once you find one, you know the sum has to be the total. So this has got to be 67 because that's what's left. And this has got to be 60 because that's what's left. Questions about that? Now, these problems tend to focus on the potential difference between A and B, this place across the bridge. Now, if there's no current flowing there, we have no trouble with doing this. If there was a line between these two and current could flow here, none of these voltages would stay like this. Because the moment current can flow there, I have a place where the current can change, and that means that I probably don't have this kind of nice stability. So what they'll tend to do to prevent this from being a problem that is unexecutable by you guys is they'll put, like I said, a capacitor here. Now, I might not know how much current flows the moment the switch is thrown, but I do know that in a steady state condition, there's no current across the capacitor. And in a steady state condition, that means whatever the voltage is between A and B would be as if there was no cable here at all. Because by definition, if there's no current flowing, it's like it's an open circuit, which would also be the same as if it was a voltmeter. So the question comes down to, well, what is the voltage between A and B? Anybody here figured that out? Oh, I don't know if I have that much longer to wait, so it's 7 volts. If we look at it, look from the standpoint of kind of like gravitational potential energy. This side is 67 volts above the baseline. And this side is only 60 volts above the baseline. If you're looking at this, both of these sides being, say, two mountains, one right next to the other, we know the height of the mountain is related to how much potential energy there is. Remember, that is voltage too. If this bottom line represents our zero voltage line or our reference point, then A is 67 volts above that line, point A, and point B is 60 volts above that line, which would mean across the center here, if I put a voltmeter here, it's going to measure a voltage of 7 volts. And it's going to tell me that that voltage is in this direction, with the left side being the high potential and the right side being the low potential. So these Wheatstone bridge problems play with the ratio of the resistances. And often these problems are going to be about what's happening between A and B. And they'll do a variety of things, but almost always what they're going to do is they're going to put a capacitor there. And don't be thrown off when they do something like this, because they'll do this too to see if they can catch you. They'll put a resistor and a capacitor in series here, which should scare you. It should scare you if they ask about what happens when you first turn the switch, because it would be really hard to calculate that. Because the voltage won't be 7 volts when the switch is first thrown, because these will not establish themselves until there's no current between A and B. But they're not going to ask that question. They're certainly not going to ask it this year. That's way too mathy. But what I would expect them to ask this year, if they're going to use a problem like this, is they can use this problem to establish your capacitive problem, giving you the voltage across the capacitor in the steady state condition. And then ask questions about how the capacitor behaves, how much energy is stored there, throw in a dielectric, things like that have to do with the capacitor. But we're within 2 minutes, so let's get the big takeaway here. In these kinds of circuits, stop always thinking that your best bet is to use Ohm's law and reduce the circuit. Start looking at faster ways to get information about the voltages. One of the things we want to work towards is finding ways to save time with those kinds of minutia problems. They're easy and they tend to be your go-to because they are easy to do. And that gives you a little bit of confidence and a little bit of comfort, but they're also not going to be very point-worthy. We want to make sure we save time for maybe some of the more tricky things we know are coming down the line. All right. I'm going to